Okay, for this screencast, we're going to be talking about Kirchoff's rules. And Kirchoff's rules are another way to analyze circuits, simple DC circuits, and try to figure out how much current there is in various branches and what the potential is across, the voltage is across various branches. You'll hear me use the word potential and voltage. In the world of electricity, electric potential and voltage are exactly the same thing. They're two words that mean, two expressions that mean the same thing. So if I flip back and forth between those, you'll know it's the same thing. Kirchhoff's rules are based upon two principles, conservation of energy and the conservation of charge. The loop rule is really more an expression of the conservation of energy, while the junction rule tends to be an expression of the conservation of charge. So there are two different rules that can be applied to help solve circuits that are a little bit more complicated. And that's that last statement there. For example, if you have more than one power supply, that tends to be a little bit more complicated than a circuit that has a single battery in it. Power supply being the battery or whatever's providing the voltage difference to drive the current. Okay, the next slide. I've actually got a little picture here of a page from a textbook that does a nice job of explaining Kirchhoff's rule, and it starts off with the loop rule. So the loop rule, I'm going to zoom in over here on this graphic here. It basically says that, and this symbol right here, this little E symbol right here is just the voltage. That's how the textbook identifies the voltage of the battery itself, is that script E. So that could be, let's say, 12 volts. Basically, it's showing there's a current that's going in this direction, and it's going across a simple resistor, and it's going in a counterclockwise fashion. And down below here, excuse me, I'm going to erase this so you can see what I'm about to scroll up to. Down below here, they've got a graph of the potential or the voltage at different points in that circuit. Pay attention to points A, B, C, and D. So if this was a 12 volt battery, for instance, that might be 0 volts, and this might be 12 volts. So you increase in your voltage as you go across the battery. Kind of like going from the bottom of a hill in a gravitational situation to the top of a hill. We've chosen point A to be the valley, or the bottom of the hill, electrically speaking, and point B to be the top of the cliff. That's the higher point, higher gravitational potential energy, in this case, higher electrical potential energy. So the graph here shows 0 voltage at point A, and then when you get to point B in the circuit across the battery, you've gone up to, let's call it 12 volts. The wire, we assume, has no losses, so there's no energy loss across the wire. You still have your 12 volts at point C. You come down to point D after you've passed over the resistor. You've lost all that energy. You've turned all of that electrical energy into heat energy, or you've done some kind of work with it. So you've converted that electrical energy into some other form, so you don't have any voltage left, no potential. So you're back down to 0, and you go to point A again. Now that's important in that simple circuit that you understand that graph, because we're going to apply that to an example problem that is basically Kirchhoff's loop rule that says the change of electric potential or the voltage across any loop in a circuit is equal to 0. Okay, and here's what that looks like in mathematically speaking or in writing. The sum of the electric potential differences, that is delta V, so that's the change in the voltage, across the circuit elements that make up a closed path, so any loop in a circuit, is 0. So if you add up all the voltage changes across resistors and batteries, they should add up to 0 for any closed loop. All right, let's look at an example on how we can use this. Okay, this is out of your book, or out of a book, not the one that we use. But I've highlighted the fact that the word potential here is really another way of saying voltage. And I wanted to highlight something else down here in this example. We'll get to it in just a second. Let me erase this. Okay, so we've got two batteries in this little circuit right here. We've got a 4-volt and a 10-volt battery. 10 volts has more energy than the 4-volt, so the assumption is that the current in this circuit is going to flow this way. Even though you've got a 4-volt battery here, let's assume that the current is going to flow in a clockwise fashion because the 10-volt battery is going to overpower that 4-volt battery, we think. So we're trying to find out what the current would be in this battery with those, in this circuit with those 3 resistors and these 2 batteries. So we have to do a little circuit analysis, and we're going to apply Kirchoff's loop rule to this. So it mentions here that to determine the direction of the current, the 10-volt battery has a larger EMF, that's just another way of saying voltage again, than the 4-volt battery. Therefore, the current in the circuit will be clockwise. So mathematically, what does this look like? This is where I'm going to erase some of the stuff and then zoom in. All right. We apply the loop rule going clockwise, okay? So notice how what they've done is they've said the change in voltage across the 10-volt battery, the 20-ohm resistor, the 4-volt battery, the 60-ohm resistor, and the 40-ohm resistor. They've got 5 separate terms there. So they're looking at the voltage change across each one of those devices. So now let's go up and look at that circuit again. So we're looking at the voltage change across each one of these devices, the 10-volt and 4-volt batteries and those 3 resistors. Notice how, try and get it so everything is in the same screen. When you're going in the direction of the current, so they're starting at the 10-volt battery, you go from left to right, you're increasing your voltage. So that's a positive 10 volts. Now I go in the direction of the current across a resistor. When you go in the direction of the current across a resistor, you lose voltage. So you're giving up that energy that the battery gave you. So whatever that current is times 20 ohms, and that's a negative sign because you're losing energy. That's the change in voltage according to V equals IR. Remember Ohm's law, so instead of delta V, I have I times R. Same thing for the, well, now I have the 4-volt battery. I'm going in the direction of the current flow, but notice how the positive terminal of the battery is on the right-hand side. So as I go from left to right, clockwise in this case, in the bottom part of the circuit, I'm actually going from the positive side of the battery to the negative side, so I'm losing voltage. So that's a minus 4 volts there. I get to the 60 ohm resistor, again a minus sign for the same reason I had a minus sign there in the first resistor, and it's a 60 ohm battery, and I have another minus sign for the I there, and that's a 40 ohm battery. So I've got one current because it's going to be the same I throughout that loop, and I've got equation now that I can actually use to solve. So let me see if I can quickly get rid of all that, all the graphics. There we go. All right. So we simply solve that now. Let's see the math here. Solve and evaluate, and they come up here with a current of 0.050 amps. And they mention here that the potential difference across a 4-volt battery is negative since we move from the positive to the negative terminal of the battery when you go in a clockwise fashion. It's important that you remember when you apply Kirchoff's rule that you have to always move in the same direction around the entire loop. And we followed the current. So we followed the current in a clockwise fashion all the way around, and when we came to that battery going clockwise, we went from the positive to the negative terminal. So we have a 0.05 amp current in that loop based on applying Kirchoff's loop rule. Okay, so we now know that the current is 0.05 amps, and the question I actually need to go back to is actually asking, predict the potential difference between, or the voltage difference between points A and B. Well, now that you know the current I, and you know you had a positive 10 volt change from A across that battery, now knowing the current and across that 20 ohm resistor, you can find that there is a 1 volt drop across that resistor. So the voltage from A to B is 9 volts, positive 9 volts. All right. The junction rule, Kirchhoff's junction rule, is based on conservation of energy. Let's look at that on the next slide. The junction rule simply says that all of the current going into a junction, and I've highlighted the junction here at this point right here, has to equal the current coming into a junction has to equal the current going out. So the current coming into that junction is I1. Current going out is I2 plus I3 plus I4. You'll notice, we've seen this before when we did our circuit analysis on a complex circuit in the last screencast. So this isn't new, but this is called Kirchhoff's junction rule. You can use, I'll do one example problem on another screencast where we combine the junction rule and the loop rule on a slightly more complicated problem, circuit problem with more than one battery and parallel resistors, which was not what we saw in that first example that I did in this screencast. It was a little more simple. So I'll combine these in another screencast and I'll do a sample problem.